Okay, this is the end of chapter 3. We're going to be looking at exponential growth and decay. We've got two different formulas you may be familiar with. I put the way the book called them, but right here is the one you're most likely familiar with. A equals P times 1 plus R to the T, and then the even more familiar, A equals PE to the RT. Okay, now R is a percent value that's been divided by 100. Okay, and if it is growth, then it is a positive percentage, and if it's decay, then it's a negative percentage, which then gives you something that is greater than 0 or less than 0. So we may recall before that if I have 1 plus some number, 1 plus some number is my base. Okay, raise that to the x. Then that's a number greater than 1. That's going to curve upward like this. But if I have 1 minus some number, that's going to give me some little decimal or fraction. Okay, that means that it's going to curve down like this. So that's the difference between growth and decay. And in a bit, we'll see how that is also related to the natural base E. Okay, we're going to look at both formulas. If someone tells us a rate, it's probably easier for us to just use this first formula right here. But if I ever have to figure out the rate myself, it's going to be a whole lot easier to use the continuous formula. So in this case, they told me that we're going to grow at a rate of 1.42% annually. Well, let me divide that. 1.42 by 100. All right, that gives me 0.0142. Oh, from now on, I can just write that as a decimal. Just make sure that I've put a 0 in front of it. Okay, now if it was greater than 10%, I wouldn't have a 0. But so there's my rate. So if I start out with my initial value, or my principal, is 110 million, and then I'm going to have 1 plus 0.0142. Okay, I want to raise that to the t. And I just want to do this once for each, so I'm just going to use t equals 10 right here. Okay, so if t equals 10. Well, that gives me 110, 1.0142 to the 10th power. Let's put that in our calculators. Okay, I had 126 point something that rounded up to a 7. Okay, that's in millions of people, so it's totally okay to have a decimal. With big numbers like this, I want everybody to agree on the whole numbers, and then just give me a decimal here. That way, if you rounded it down to 6 or up to 7, we won't care if it's one or the other as long as they're close to each other. Okay, so then let's see what happens when we try to do this continuously. We're going to do 110 e to the 0.0142 t. I'm going to put 10 in there. Okay, so that's 110 e to the... So I could actually multiply this number by 10, or I can just put 0.0124. I'm going to write it with parentheses here, but you don't have to. I just want to show you that it's multiplied together. Let's figure out what that comes out to. Oh, so that gave me 126 point something that rounds up to 8. So what we see here is that the continuously grows faster. Okay, now if I want to know actually how much faster it grows, what I could do is I could pull out this e to the 0.0142, separate that out from the t, and make it look like the other one. So let's do in our calculators just e to the 0.0142. That gives me something really familiar. 1.0143. Oh, that looks an awful lot like that, but it was a little bit bigger. Okay, so any continuous rate they gave you is going to be similar to an annual rate, but it's actually going to end up being a little bit bigger. That's because we're compounding continuously instead of waiting till the end of the year. If this were money, it would be as soon as we earn a little bit of interest, we can start charging interest on that interest, whereas the annual would have to wait until the end of the year to start charging interest on that interest. Okay, so now I had said before that we could have a negative rate. If it says declining at a rate, okay, that means that our rate is a negative number. R equals negative 0.06. Okay, so that's important. If I do 12,426 people, and I've got 1 minus 0.06 to the t, and let's just go with 10 years here. We'll do that 0.94. That's where we've got a number that is less than 1, so the exponential function will look like that. And I'm going to put in 10 right here. Let's see what that gives us. So that gives me 6692.8. I know I can't have 0.8 of a person, okay, but I'll put it there so that way if we round it, we at least know where it came from. Okay, let me try the other one now. I'm going to do 12,426 e to the negative 0.06 t. So that's 12,426 e to the, I'll just put those together in the exponent with a 10, and let's see what that gives me. Okay, so that gave me 6819, okay, 0.5. Hey, that was also bigger than that, okay? However, remember, we're actually trying to decrease. We're decreasing down from this amount that we started with. So what that means is that the continuous, okay, it increases faster when you're growing, but it decreases more slowly when you're decreasing. Okay, so that's a good thing to remember. Now let's see if we can make predictions about when we reach a certain place. Okay, so I know these two aren't exactly going to be the same. What I want to focus on is what is the algebra that we do. So I've got, going back to my annual rate, so normally if somebody just told you the annual rate and wanted you to make a prediction, this is how you would do it. We'll put 0.94, so 1 minus 0.06, okay, to the t, and I want it to equal 10,000. So I need to solve this, and the way I'm going to do it is I'm going to divide by the coefficient first. Always divide first by the coefficient. That canceled. Now what I can do is I can take the natural log. And the reason I want to do that is taking the natural log allows me to bring down that power, like I'm chopping down a tree. Okay, so here it comes. There it went. And now what I want to do is divide by the natural log of that base. This looks ugly, but your calculator should be able to handle it. Okay, so the amount of time it takes to get from 12,426 people to decrease down to 10,000 people, let's see if we can calculate that now. Okay, so dividing that, those are natural logs I used. However, I could have actually put LOG in both of these places, and I would get the same answer. If somebody asked, you could use LOG. I'm just used to using natural log. And in the next example, we'll see why. But in this case, it didn't matter. Okay, the t was equal to 3.5 years. Now let's see how I would solve the other one. I'll start with the same coefficient. I've got e. It's to the negative 0.06 t, and it's equal to 10,000. This starts off exactly the same way. I divide both sides by the coefficient. Now when I natural log both sides, what happens is that this exponent here, negative 0.06 t, okay, comes and lives down in front. Okay? Natural log of 10,000 divided by 12,426. Now here's why natural logs are so powerful. If I'm using base e from the continuous formula, what's the natural log of e? Yeah, the natural log of e. What power do I raise the base e to get e? 1, good. It turns into a 1, which means that for multiplication purposes it's gone. It just canceled out. Okay? Now the only thing I have to do is divide by the rate. So that's the power of natural logs and the continuous growth formula, is that I can just do the natural log of what I want divided by what I have, then just simply divide it by the rate, and it will give me the time. And so I ended up getting 3.6. Okay, so like I said before, whether you're growing or you're shrinking, you'll always have a larger value coming out of the compounded formula. That means growing faster, but it means shrinking slower. So yeah, it took a little bit longer using that formula for us to get down to 10,000 people. Okay, now, so like I said, if somebody gives you the rate, probably best to use the original formula. It wasn't too hard to divide by the natural log of 0.94. But if you ever have to come up with a rate on your own, PERT is going to be your friend. Okay, PERT is what we use when we need to find a rate in particular. Okay, so here I have no rate. I only have a year, and I have how many cases of chickenpox we have. So let me write a PERT equation. 190.9 E to some rate times some number right here, some time. Okay? And that needs to equal, what do I end up with? 32.2, okay, thousand cases. Now, the time that elapsed was the difference between these 2 years. So how many years elapsed? 25. Okay, I'm going to put a 25 right in there. Okay, so now I can divide by 190.9. Cancel it. Take the natural log of both sides. Gives me 25R. Where did the E go? I took the natural log of it, so it's gone. Natural log of 32.2 divided by 190. Okay? So natural logging a base E just disappears that base entirely. Okay? It's almost like Mr. Sandlin's log chopping axe turned into a chainsaw with a wood chipper attached. Okay? So now I want to divide by 25, and that should give me my rate. So we got a negative rate, which is totally acceptable because we were expecting to lose cases of chickenpox. The number of chickenpox cases are going down. So there's my rate. Now I can use it to make a prediction. So I'm still going to start with 190.9. I'm still going to use E, since that's where I got it from. I want to solve for T, and I'm trying to get 20, and we're counting in thousands, so I'll write just that as the number 20. So 190.9, divide both sides, natural log both sides. After a while, you start to see the pattern, and by the time you're done, you might be able to just plug stuff into a formula. Okay, natural logging that took it away, and then dividing by the rate. Okay, so I had a rate right here. I'll go ahead and write it. Divide it by the same rate. Cancels it out. Okay, so I'm starting to see a formula here that I could, if I really wanted to, memorize. The natural log of what I'm trying to get divided by what I started with divided by the rate will give me the time. Okay. It's actually the same algebra as finding the rate, since they were multiplied together originally. Okay, so 31.8 years. Okay, so that would be in 2011, sometime later in the year. Here's one with growth. I went ahead and made a note that said that 1990 is going to be year 0, and 2000 would be year 10. Okay, but you also could have just done it in the abstract and said, let's just let the time elapse to be 10 years. So we'll find the rate now. We started with 1.94 million people in Miami-Dade County. E to the, okay, I have some sort of rate, but it's times 10 years. Okay, so I'm just going to put the years in front. I end up with 225, and now I need to solve. Okay, cool. You know what? I've gotten so used to this pattern that I know I'm going to divide, I'm going to logarithm, and I'm going to divide again, so I just wrote it like that. Save myself some space. That gave me my rate. Was 0.015, okay, 1.5% growth. So now I want to know how long is it going to take to get to 2.7 million. So I'll start off with 1.94 e to the 0.015 t equals 2.7. All right, let's see if I can jump ahead to that using the same pattern. 2.7 is divided by 1.94. I natural log both sides, and then I divided by the rate like that. Good. Okay, so I divided by the rate, and I got the amount of time. Okay, so here's something that also has a shortcut. Say I wanted to figure out the rate for how long it took something to double. I don't actually need to know what I started with to set the problem up. I can say that I want 2p where p is my principal. Now if I divide both sides by p, if I divide both sides by p, it cancels out, and it really just gives me 2 equals e to the RT. R is the rate. My book wrote it K, but I'm going to replace it with R. And T in this case is the doubling time. That's given to us. So if I want to know the rate for a doubling time of 15 minutes, I can say 2 equals e to the 15R. What do I do to both sides? I don't divide by e. I take the ln. There we go. So that gives me 0.046. Cool, there's my rate. That's how fast these bacteria are growing. A continuous rate of 4.6%. How many will there be after 55 minutes? Well, I just started with 1. E to the 0.046 times 55. Yeah, the question was, why is that 1 times E? Yeah, it was, because they told that I started with 1 bacterium. Oh, bacterium is the singular of bacteria. Cool. So then, all right, yeah, so I just want to figure out what that is. That's 12.6. Cool. Okay, that was just, we were just evaluating. Interesting part here comes, how long is it going to take to get this many bacteria? I've got E to the 0.046 T equals this large number of bacteria to clear up an oil spill. I take the ln of both sides. Gives me 0.046 T equals ln of 8192. This is easy because I only started with 1 bacterium, and that gives it to me. 195.9. 195.9. So it's going to take me a lot of minutes to get this many bacteria. So this also works if you want to end up with half of what you started with, okay? So if I'm given a half-life of 5.73 thousand years, I can do e to the 5.73 times r equals 1/2. Natural log both sides and then divide. I get the natural log of 1/2 divided by 5.73 should give me my rate. And this is actually a pretty fast rate. It's negative 0.121. That's negative 12%. Okay, so be aware, you won't always have a 0 after the decimal. If it's a bigger number, then you won't have the 0. Okay, how much do I end up with if I start with 7 grams and I want to let it decay for, decay at this rate, 0.121 for 12.82 thousand years? All right, well, let's find out what that is. So I end up with only having 1.48. Okay, I'll actually write that instead of 1.5, just to be a little more precise, because I'm down to some fairly small numbers. I just had a single number there. Okay, that's how much I have. All right, now let's see how long it's going to take to get down to 1 gram. There's not a whole lot left after 7 years, but remember, this decays in proportion to how much we have, so its decay is going to slow down. Just like exponential growth speeds up the longer it goes, exponential decay slows down, okay, as we go. So we'll set 7e to the negative 0.121 t equaled 1. I'm going to divide both sides by 7, take the natural log both sides, and then divide by the rate. Okay, so see, I'm kind of skipping steps here because I've done the exact same steps so many times in a row now. Okay. Yep, so I get 16. This is measuring thousands of years. So if I found something organic that was supposed to have 7 grams of carbon-14, but it turns out when I dig it up it only has 1 gram, then I know that it was 16,000 years old.